Welcome back to another lecture of the Elements of Sustainability series. Today's topic is one that we can all relate to. With the amount of information and misinformation in the internet, making decisions on what is safe or not for us and for our families can become overwhelming and even scary. Fortunately, today, we have Dr. Solomon to talk about chemicals in our environment, perceptions, hazards, and risks. Professor Keith Solomon is Professor Emeritus and Associate Graduate Faculty in the School of Environmental Sciences at the University of Guelph. He's also Director of the Center for Toxicology. Professor Solomon teaches in areas of toxicology and pesticides at the University of Guelph and advises graduate students. He directs an active program on research into the fate and effects of pesticides and other substances in the environment, exposure of humans to pesticides, and industrial chemicals and risk assessment. He has and continues to serve on several advisory committees on matters related to environmental toxicology and pesticides in Canada, the US, and internationally. He is a member of the Society of Environmental Toxicology and Chemistry, the American Chemistry Society, and the American Association for Advancement of Science. He is the recipient of the 1993 Society for Environmental Toxicology and Chemistry, ABC Laboratories Award for Environmental Education. Was selected as a Fellow of the Academy of Toxicological Sciences in December 1999, and is recipient of the 2002 American Chemical Society International Award for Research in Agrochemicals. In 2006, he was awarded the CTAC Europe Environmental Education Award and the Society for Environmental Toxicology and Chemistry Founders Award. In September of 2013, he was the Sterling B. Hendricks Memorial Lecturer, an award sponsored by the U.S. Department of Agriculture, Agricultural Research Services. In 2014, he was elected as the Fellow of CTAC. He is co-author of the book Pesticides and the Environment, which has been translated into Spanish and Portuguese and is used as a teaching text at the University of Guelph and in a number of universities around the world. Welcome, Dr. Solomon, to the series. It is an honor to have you. We are ready for your lecture.
Thank you, Erica. It's my pleasure to join you in this lecture. The topic I'm going to be talking about is chemicals in our environment, and this relates to perceptions, hazards, and risks. And starting at the very beginning, I'm going to go to the planet Earth, which is composed completely of chemicals. And every organism on this planet, including us, is also composed of chemicals. These chemicals were formed after the Big Bang, and they now are a part of everything that we do and everything that we work with. So fear of chemicals is given the official name of chemophobia, and there's a couple of definitions here. The one from the International Union of Pure and Applied Chemistry is an abnormal or excessive fear of chemicals, and there are many other ones in dictionaries. And the question is, why, when we are made of chemicals, when our entire environment and all the things that we do and use are made of chemicals, why should we be so concerned about chemicals? And I don't know the exact reason for this, but I believe that it's probably driven by a lack of understanding and knowledge of chemistry and chemicals. Lots of students in high school and even at university are scared of chemistry, but if you do develop an interest in it, what you find it's an absolutely fascinating subject that is very much related to everything that we do every day. All the chemicals that exist on the planet and in our bodies are made up of elements, and there are 118 elements that have been identified so far. And just as an example, the human body is about 65% oxygen, 18% carbon, 10% hydrogen, and there are another 4% of other elements as well. Now, chemicals have properties that fall into two general categories. So every chemical has intensive and extensive properties. So looking at intensive properties, these are independent of the amount of chemical there, but they relate to how the chemical behaves in the environment and how it interacts with organisms in the environment as well. So things like, is it soluble in water? Is it a solid, a liquid, or a gas? How dense is it? Where will it move in the environment is driven by these intensive properties. And more importantly, from a toxicological point of view, will it react or combine with other chemicals or with receptor sites in organisms in the environment or humans as well? And intensive properties do not depend on the amount of the chemical that is present. They are imbued in the actual molecule. Each individual molecule has the same intensive properties. Extensive properties, on the other hand, are related to the mass and the energy and the volume of the substance, and also to the toxicity. And this is an important point to remember, is that you might have one molecule there, but in order for it to be toxic, you usually have to have a lot more than just one molecule present in a system. So toxicity is an extensive property, and it relates to the number of molecules or the concentration or the dose, but related directly to the exposure that the organism experiences to this chemical. This is not a new observation. This is a painting of Theophrastus Bombast von Hohenheim, also known as Paracelsus, and he lived in the 1400s to 1500s and was probably one of the early chemists, and he was a medical doctor as well. Painting here, painted by Peter Paul Rubens and hanging in the art gallery in the city of Brussels. But he made an observation that was written down in a book that he wrote, and that was here translated directly from German, so it's got lots of negatives in it. But basically what he said was, the dose makes the poison. And really, if there's no exposure to a chemical, there's no possibility that it'll be poisonous. But almost any chemical can be poisonous if you have a large enough exposure. So nothing is really safe except when we consider the dose and the amount of chemical that you're exposed to. So looking at this in a diagram here, we have toxicity, which is related to the intensive properties of a chemical. And on the other side, we have exposure, which is related to extensive properties, or how much chemical is there. And the overlap between these two circles is hazard. If there's no overlap, if there's no exposure, or there's a very low toxicity, then there will be very small hazard. If there's high exposure and or toxicity, obviously we'll have a much greater hazard from these chemicals. So just to go back a little bit here, for every chemical in any organism, and that includes humans, there's a high dose that could be lethal. There are lower doses that might cause chronic adverse effects in organisms in the environment or in humans. And there are still lower doses that might be stimulatory or beneficial. And in that category, we might have drugs or pharmaceuticals that we use to improve our life and our health. Obviously, a large dose of a pharmaceutical can be hazardous, but small doses may cure a disease or make a condition less severe. And for all of these chemicals, there is still a lower dose that will have no adverse effects. Just a couple of little pictures here. These are old ones. This is a nerve food that was probably sold to students at the turn of the century to help them get through their exams. But when you look at the side of the container, what you see that each pill contains strychnine, which is a natural poison coming from plants, and arsenic, which is an element that is also toxic. At these very small doses, it didn't kill the people, but it did perhaps make them a little bit more alert or improved their metabolism because of the effect of arsenic on metabolic processes in the human body. There's some other examples here. This one was told to me by Sir Richard Doll, who was one of the persons who linked cigarette smoking to cancer of the lungs. And he pointed out in a lecture that I attended that alcohol consumption has benefits at low doses and adverse effects at high doses. And this was a graph that he used to illustrate this, and I'm just showing this graph. But at small doses of alcohol, you get a benefit in terms of a reduction of the risk of coronary heart disease and stroke. And that's because alcohol has beneficial effects in the bloodstream and reduces clotting and other responses in the blood. However, if you take too much alcohol, this increases the risk of esophageal and stomach cancer. So there's kind of a happy medium here. This is illustrated by the yellow graph. You get a reduction in total mortality if you combine these two causes at low doses, and you get an increase at higher doses. And the low dose that is beneficial, at least in men, is 2 glasses or equivalent to 2 glasses of wine a day, and in women maybe a little bit less, like 1 glass. He hastened to point out, by the way, that you have to consume it every day for it to be beneficial. But if you save it up for the weekend and have 14 glasses on Saturday night, this will not be very healthy for you. Just to also focus on another point, that people are often confused by natural and synthetic compounds, and there's a belief in the public, perhaps, that natural compounds are safer than synthetic compounds, and this is really not true. The most toxic substance known to humans is botulinus toxin. It's a protein product produced by bacteria, and it causes food poisoning in improperly preserved meats and other protein-containing foodstuffs. It's the most toxic substance known to humans. If I had a couple of kilograms, in theory, I could kill every person on Earth. And yet, Botox, which is its drug name, at very small doses has medicinal and also cosmetic uses. And I found an advertisement on the web showing the benefits of Botox injections in terms of removing frown lines from this model in this particular illustration here. And many people out there use this to improve their looks and other things. So most toxic substance known to humans is beneficial in very, very small doses. So there are also some other examples that I'd like to illustrate here. These are on the left-hand side of the slide, are a group of synthetic chemicals, and they range in toxicity, and this depends again on their intensive properties. So fentanyl, which is involved in many of these accidental overdose deaths of people using opioids, is extremely toxic, and a very small amount will take you over the toxicity threshold, and you'll stop breathing and die. But aspirin, that we routinely take for a headache, is also potentially toxic. A fairly large amount will cause harm. If you consumed a herbicide like 2,4-D, a larger amount still would cause harm. And just as another example of a synthetic chemical, glyphosate, another herbicide, it's very hard to kill animals with glyphosate, and the toxic dose, at least in rats, is much higher than the highest number that they've tested. On the right side is botulin, which is a natural compound. Strychnine, another natural compound that we saw in that earlier slide showing the nerve pills. Caffeine, we all routinely drink tea or coffee or other stimulatory drinks that contain caffeine. 10 grams of caffeine will harm you. It's equivalent to 118 cups of coffee. I don't think there's any danger of me suffering from caffeine poisoning. I don't drink that much a day, and I don't know anybody else who does. Alcohol is poisonous. Sugar, 3 kilograms of sugar will kill you. And there's a case of a woman who was joined in a competition, a water drinking competition. It sounds crazy, but she consumed 6 kilograms of water and died as a result of that, because the water diluted the salts and other essential elements in her blood. And she died of respiratory failure because of that. So there's really nothing out there that's safe or completely safe, but really it is the dose that makes the poison. Also, perception drives the fear of the unknown. And when you, as a chemist, I look at the name of a chemical, 2-acetobenzoic acid or N-phosphonomethylglycine or sodium hypochlorite, and then I understand what those mean. But the general public, people who are not very familiar with chemistry, see these names and they don't understand them, and that probably engenders a certain amount of fear. Well, the first one there is aspirin, we talked about earlier. The second one is glyphosate. And the last one is bleach, which is you'll probably find in everybody's laundry and is certainly used in commercial laundries as well. And all of these obviously can be toxic, but again, it's the dose that makes the poison. And as long as you don't exceed that poisonous dose, there is no hazard to these chemicals. And I just wanted to point out that I talked earlier about everything on Earth being made of chemicals, but the food we eat is also made up of chemicals, as we are made of chemicals. And I've got a photograph here of some all-natural strawberries. And these were, a photograph came from Professor Kennedy from Monash University, I think it is, in Australia. And what he's shown here is that if you put the chemical names of the compounds that are present in a strawberry that we would quite happily pop in our mouths, some of these look kind of scary, and you can see lots of names there, and also some code letters. Just for instance, preservatives. These are natural preservatives, not synthetic preservatives, but they are given a letter, and also colors that are natural colors that we often add to foodstuffs to improve the appearance. And again, these are numbered here as well. So this is just a simple strawberry, and you can see there's a whole list of chemicals in there that we can consume, and we can use to build proteins and other things in our bodies, as animals can as well. And you can look at other foodstuffs like an all-natural peach, containing, again, a whole list of chemicals that have names that seem to be a little bit frightening if you're not a chemist. And then even a lemon. So the lemonade you drink contains most of these chemicals, and we don't suffer injury or anything else from drinking lemonade. Here's another example now. This is something that The chemist would look at this and interpret this as, first of all, it's a chemical. It's got sugars on the left side, and it's got some other structures on the right side. And I would look at this and say, well, that looks very soluble in water. But what it is, in fact, is a constituent of potatoes. And it's called solanine, and it's toxic in humans. The dose that would cause toxicity is not that small. 7.5 grams might be toxic in a human, but this is a natural pesticide, and it is produced in potatoes to ward off insects that would eat the potato. Most of these solanines are found in the leaf of the potato. And here's a photograph of a Colorado potato beetle feasting on the leaf of potato. And this chemical is produced in that leaf in an attempt to discourage the Colorado potato beetle. On the right are some potato tubers, and these tubers also contain solanine. Most of it's in the skin of the tuber, and the amounts are much smaller than they are in the leaves. So you can consume potato tubers after they've been cooked, and they will not harm you for two reasons. One, there's not much solanine in the potatoes, and secondly, when you cook them, the solanine is extracted from the water. If you're boiling the potatoes, it's extracted into the water, and if you throw away the water, you're actually getting rid of any exposure to solanine. Now, unfortunately for the potato, it tries to defend itself when it's attacked by insects, and a study conducted here at the University of Guelph showed that if they're attacked by potato beetles, they increase the production of this natural chemical, solanine, in an attempt to ward off the damage caused by the potato beetle. But unfortunately for them, the potato beetles have evolved resistance to solanine, and this doesn't actually harm the potato beetle. But if you consumed the potatoes from a badly damaged plant, some of those potatoes might exceed the guideline level of solanine for protection of human health. So in this case, there's a trade-off here, perhaps between natural chemicals produced by the potato plant itself or synthetic ones that are sprayed on the potato by humans trying to grow potatoes. And in this case, the net benefit is when you spray synthetic pesticides, you reduce the risk from potatoes that in some situations might be harmful. Natural pesticides, and there are many, many natural pesticides produced in plants. In fact, Bruce Ames in 1990 published a paper where he stated that pesticides are 99.99% natural. And what he was referring to were these chemicals such as solanine and other products that are found in plants that protect them from herbivores, not just insects, but also other herbivores. So, of course, we need to ask ourselves, well, what happens to these natural pesticides when they are in our food and we eat them? Well, fortunately, animals have, over the many millions of years of evolution on this planet, have learned to live with plants, and also with plants that are potentially toxic because they produce these chemicals. Just a picture here of a liver and the intestine, and also the blood supply that takes absorbed food from the intestine into the liver. So when you eat something, the nutrients are absorbed, and of course the other chemicals that are present are absorbed as well. And these are transported directly to the liver. And in the liver, there's a series of enzymes that are specially designed to remove harmful chemicals from the blood that we might take in from our natural food. So the gut is where the food is digested, and then it's transported to the liver in the hepatic portal veins. And in the liver, these chemicals are broken down by enzymes and metabolic processes. And the chemicals are then either converted into something that we can use in our own bodies, or they're excreted via the kidneys. And the important point here is that almost all synthetic chemicals are also broken down in the same way. So what protects us from natural pesticides in our food also protects us from synthetic chemicals that we may be exposed to via food or our environment or the work we do or the water we drink. So I wanted to just change gears a little bit here and talk about hazard and risk. And there's often confusion about hazard and risk. But in a sense, all things can be hazardous. And I've just put a few examples here. Climbing mountains or being a mountaineer is probably the most dangerous sport that you can be involved in, because more people die in mountaineering accidents than in any other accidents associated with sports. And of course, we all know that every day people are killed in automobile accidents. Sometimes people are killed directly by the physical effect of choking on food. People die of overdoses of drugs, and people die of electrocution. So all these things can be hazardous, but in many cases, we quite happily get into an automobile, we quite happily eat food, we quite happily take a pharmaceutical if it has benefits to us, and we switch on our electricity, even though electricity itself can be hazardous. And risk is something different. And a little bit of history here, and it's kind of neat. Some of these names people might recognize if they have scientific backgrounds here. Blaise Pascal was a mathematician, and at least in Canada, we use the unit Pascal for measuring pressure, such as in the tires of our automobiles. Jacob Bernoulli and other scientists, Abraham de Moivre, and Anthony Arnauld were all scientists working in France in the 1600s, and they were the pioneers of a lot of the modern mathematical processes that we use nowadays for computer calculations and modeling and other things. Abraham de Moivre actually described the normal distribution, and I'll talk a little bit more about that because that is part of an understanding of what risk is. Anthony Arnauld actually wrote a book called the Port Royal Logic. It's called the Port Royal Logic because these people worked in a monastery at Port Royal in Paris, which is now a metro station on the Paris metro network. The monastery is long gone, but fortunately, the books that were written are available, and some of these are translated into English. And I wanted to just show you an excerpt from the Port Royal Logic. And this is talking about people being scared of thunder. I guess I'm not scared of thunder, but I am scared of lightning. And I take precautions, like not standing under a tree when there's a thunderstorm in the area. And then what he's saying here really is that the fear of an evil, in this case lightning and thunder, ought to be proportionate not only to the magnitude, of course lightning is very big and the sound is very loud, but also its probability. And actually very few people are killed by lightning every year. Few people are, but the probability of being killed by lightning is far, far less than the probability of being killed in an automobile. And yes, most people will be very concerned and scared about lightning, but not of getting into an automobile. And what he was really talking about here was probability, which his friend Abraham de Moivre had described in his book on the doctrines of chance. And this was really the first time that this term was used in relation to risk. But everything we do and everything that happens to us in our lives is driven by probabilities. And part of probability is the normal distribution. And this is a picture of a 10 Deutschmark note, which was what was used in Germany before it joined the European Union. And the picture here is of Carl Friedrich Gauss, who some of you will know from the name of the distribution illustrated on the left of the banknote here, which is the normal distribution and the formula for the standard deviation, which is a characteristic of a normal distribution. And he was a professor of mathematics, and he described this. And this note actually gave statistics students a chance to cheat by opening their wallets and pulling out this little formula during an exam. Now, jokes aside, the normal distribution looks like this. And if we put numbers onto it, these numbers look like this. But really, everything that we do, the chances of a building collapsing is governed by probability calculations by engineers. The insurance policy that we pay for every year for our car, the premium is covered by the probability that we will have an accident. The insurance, again, that we pay for life insurance is again governed by the probability that we'll die before a certain age. And, even maybe some people's intelligence, as is illustrated by this cartoon, some people are pretty low down on the door of the distribution of intelligence, and others are much higher up. And just a very simple thing like height. If you look at the height of individuals, they can be put into a cumulative frequency distribution that I've illustrated with this little cartoon here. And some people are relatively short. Some people are very tall, and these are the people who can become basketball players because they stand head and shoulders above normal people. And this makes it much easier for them to get the ball in the basket. On the other end, you might find people who can be very good gymnasts because they're smaller and they weigh less, and they're much more agile than the other people on the distribution. But when I buy a shirt or a pair of pants, the size that I buy, the availability of that size is determined by measurements of the population here in Canada or in the United States that allows them to figure out how many size large or extra large or medium or small to satisfy the sizes that are out there in our population. And then I quite often ask the toxicological question here of students when I'm giving a lecture, and I say, well, how many of you take, how many people feel happy after one drink? And a few people will put up their hands. Other people will wait until I say 2 drinks, and then the number of hands slowly go up until, at least at university students, I have to get to 8 or 16 drinks before they say they're really happy. But what this really shows is that sensitivity to chemicals, in this case alcohol, also follows the same kind of probability distribution. Some people are very sensitive, and other people are much less sensitive. And if you know this, you can use this to calculate risks from chemicals, especially if you know the exposure that these people are subjected to. So here I can interrogate this distribution in a sense and say, well, how many people are shorter than or taller than a certain value on the x-axis of the graph? And I can use that in a predictive way to say that if I go back to that population, I'll find 40% of the people will be taller than 5 foot 6 inches or whatever that number happens to be. The same thing happens with carcinogens. This is data taken from updates in an original paper by Lois Gold, where she looked at the same kind of distribution, although this is the normal Gaussian distribution, looking at carcinogens. These are ones that have been shown in laboratory tests, chemicals that will actually cause tumors in laboratory animals. And what she's showing here in this data is that this can be described by a normal distribution. And you can use that if you have a chemical that hasn't been tested to say where it's likely to fall in this particular distribution. Is it going to be to the right and require very, very high doses to be a carcinogen? Or is it going to be on the left and be carcinogenic at smaller doses. But probability tells us that below a certain dose, and especially with what we know about metabolism in the body, that there are doses below which even cancer-causing substances will not cause cancer. So if we go back to the diagram that I used to illustrate what Paracelsus said about the dose makes the poison, when we talk about risk, what we need to overlay on this is the likelihood or the probability that you will be exposed, or that the chemical you're exposed to, you'll be very sensitive to it. And the overlap of these three circles here then illustrates risk. And to go back to a more traditional way of showing that using the normal distributions, if that's a distribution of exposure values for a chemical in food or in air or in water or in our environment, and I then take this chemical and see where it falls on a distribution of toxicities, just as we saw in that distribution of tumor-causing chemicals that Lois Gold developed. The overlap between those two graphs is the risk. And this can be mathematically determined more easily from this kind of data than it would be from the Venn diagram that I showed you earlier. And obviously, if I change the exposure here, even if a chemical was potentially toxic at one exposure, it might not be at another exposure, or the risk might be very much smaller at that smaller exposure. So when we talk about regulation of chemicals, if they do have toxic properties, if their intensive properties make them toxic, then we can reduce the risk by reducing the exposure and controlling how the chemical is used in the environment or in our food or whatever else. So chemicals are regulated. These people work for government departments in the United States, Food and Drug Administration, the Environmental Protection Agency, in Canada, Health Canada, and the Pest Management Regulatory Agency. And they require toxicity data for pesticides, pharmaceuticals, and industrial chemicals. They also require exposure data, and they use that using the precautionary approach. They use it for safety factors to protect humans and the environment. So although we do have chemicals in the environment that could be toxic, our regulatory systems are well developed, and we are protected from harm from these chemicals by regulations that restrict access to these chemicals, to train people, etc. So in summary, all things on Earth are made of chemicals. Chemicals are composed of combinations of elements, of those 118 elements in the periodic table. There's a huge range, or vast range, of chemicals that have very different physical, chemical, and biological and toxicological properties. Toxicity is a combination of physical and chemical properties and exposure, and some chemicals are essential for life. Most of them are innocuous at the exposures that humans and other organisms experience, and there are very few of them that are dangerous and that need to be regulated to keep exposures below the threshold of harm. So I hope I've helped you understand a little bit more about chemicals and hazard and risk. And thank you for this opportunity to present this webinar. And I'm happy to answer questions from anybody by email, or I believe Erica might have a few questions for me. So I'll hand this back to her. Thank you.
Thank you, Dr. Solomon, for bringing some clarity to such a debated topic. So some of the questions, let's start with how does perception relates to sustainability?
Well, sustainability is a very important part of of human activity on Earth. We're threatened by all sorts of things that we do. Not all of them are related to chemicals, but just to live in a sustainable world where our children's 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 children, etc., will have a lifestyle and a quality of life that's as good as ours, we need to do things sustainably. We need to grow crops sustainably, and we need to make chemicals that we use in our daily life, whatever they're used for, we need to make them as sustainably as possible because we want to be able to continue doing that into the future. So chemicals are necessary for everything that we do. And the perception that chemicals are harmful is not true for all chemicals. In fact, it's only true for a very, very small proportion of chemicals. And we can continue to use these chemicals sustainably, provided we look at life cycle assessment. That's been a topic of other lectures in the series. But we also look at the risks and dangers posed by these chemicals and do that in a rational way and realize that things are regulated. And as long as we're careful, we will not suffer any harm from these chemicals.
Okay, so when it comes to green chemistry, how does it fit into the sustainability framework?
Yeah, well, again, green chemistry is more related to how you make the chemicals, because you can't change the properties of a chemical. These are intensive, and they belong to the way the chemical is made up and how the individual elements in that chemical are linked together. And those properties can't be changed. You can use different chemicals that have different properties, and that's one aspect of green chemistry. So, use, for instance, if you're using a pesticide or a cleaning agent, use the one that causes the least side effects in humans or the environment or whatever. And that's a green approach to selecting what chemical you use. But if you need a chemical for its specific properties, if you need aspirin to control a headache, and you don't want to use some of the other alternatives, you can't really get that effect without using aspirin. But just use it carefully. But if you make aspirin, make it in using the green chemistry. In other words, releasing fewer byproducts to the environment, consuming less chemicals, and releasing fewer chemicals to the atmosphere, such as CO2, etc. And that's what green chemistry, I think, is all about. And it's very important that all our chemistry should be as green as possible. But if we're looking for a chemical that has a specific use or a specific property that we need, it's hard to change that without changing the chemical and maybe exposing us to other properties that are potentially harmful as well. So green chemistry is great, and I'm all for it. And I would support green chemistry very strongly.
Okay, so you were talking about the dose makes the poison. Are there instances of people that have been harmed by natural chemicals in our food?
Yeah, and in a sense, just to take a very simple one, most people, not everybody, but lots of people, especially university students, have suffered from hangovers. And while a hangover it's not lethal, even though you wish you were dead, maybe, but it's not going to kill you. But that's from excess consumption of a natural product, and that's alcohol. Alcohol is a natural product. It's made by yeast from sugars, and it's a natural product. But there are some other chemicals that have caused harm. Potatoes, just to go back to the example I used earlier, the solanine in potatoes in the tubers increases if the tubers are exposed to light. So if you see a very green potato tuber, then you can be fairly sure that there's lots of solanine in that tuber, and I strongly advise against eating it. There was a case many years ago in India of people who ate green potatoes, and it actually killed some of those people, and the others were made very sick. And there was another example of zucchini, which had been bred to be resistant to pests, insect pests. So it had lots of natural pesticides in it called cucurbitacins. And this product, this new strain of zucchini, was grown, and it was put into cans by a canning company in California, and it made a lot of people sick. They had to recall all of the canned product because it had too much of this natural pesticide cucurbitacin in it. So yeah, these things can sometimes happen, and we learn from these errors, and I don't think that sort of thing would happen again. But do be careful of green potatoes because they may make you ill, if not kill you.
Good. And so you were talking at the beginning of the lecture about chemophobia and basically how it is increased by the lack of knowledge on chemistry science in general. And knowing, that all of us have to make decisions to purchase products made of many chemicals, and we have this concern about health and safety for ourselves, for our families. How do you recommend us to look at those ingredients, or what we can do to feel better or more informed about that purchasing decision without following the alarming news that sometimes we see on threads online?
Yeah, and the internet, unfortunately, is it's not a curated database of toxicity information for chemicals, which is very unfortunate because it means there's correct information there and there's incorrect information there, and it's sometimes difficult for untrained, inexperienced people to separate the two. But just think back to those pictures I showed you of, strawberries and lemons and peaches, and you saw that huge list of chemicals in there, and these are natural. Nothing in that was artificial. These peaches and strawberries were grown totally naturally. And recall that our bodies are able to get rid of these chemicals. And yes, people are required in some jurisdictions to label products with what they contain. And I would encourage that labeling, especially for pharmaceuticals. I'd like to know what's in the pharmaceutical. I'd also like to know what's in the pesticide that I might buy to protect my food plants in the garden as a farmer. And, if I'm using foodstuff that is prepared commercially, I would also like to know what people have added to it. But we know the properties of these chemicals, and the food chemists who work for the companies, large companies who produce these chemicals are knowledgeable in this area. And almost all issues around food harming people through chemicals in the food is related more to chemicals produced by bacteria. So toxins produced by bacteria when food goes off, or actual infections that result from eating food that contains bacteria like Salmonella or E. coli. And in fact, quite a few years ago, I ate some tuna that had histamine in it, which was produced by bacteria that got into the tuna after it was caught. And several of us had to be hospitalized because of that. And that was a natural chemical produced by bacteria in food. And probably 90% of issues, or more than 90% of issues related to food, are related to bacterial or fungal or other natural problems in the food.
Okay. So one more question. We have hundreds of thousands of chemicals out there, and we have regulations that might address all or not all of them. And as our Professor Lefsrud is going to talk later this week about that we live in this post-truth, post-trust, post-reality era. And the point is that it seems that all these regulations, all the hazard assessment that is being done by experts becomes very difficult for the general public to understand what is happening. And given the lack of trust that is growing within people, what do you think we can do in both as an industry or as an informed consumer to increase transparency and build that trust bond back again?
Yeah, that in fact, there's another book written by an author from California named Farhad Manjoo, and the title of the book is "Living in a Post-Fact Society." It's true that there's a lot of concern out there, and part of it is because these facts are so easily, researched. I can search stuff on the internet, and fortunately, I have the background to be able to sift, at least in the toxicology area, the facts from the mistruths, and but the general public doesn't have that. And then, of course, I can very easily say, because I'm an educator, people need more education, because that'll ensure my job and the job of the people who take over my job when I eventually step down. But people should seek out information, and they should seek it out from what I would call reliable sources. So, as I tell my students when they write a term paper, you can use internet sources for data, but you have to evaluate that data critically. You can't just accept it. And I will allow you to use internet references in your term papers, but I don't want to see a .com at the end of any of those references. I want to see .org or .gov, G-O-V, because those sources like scientific societies or universities, edu, or government websites, I think the information they have is much more, it's certainly curated, and it's been evaluated, and it's certainly much more useful information than the rest of the 90 or 99 or whatever it is % information that you can get by using a simple search term like toxic on the internet. So I hope that helps.
Yeah, this has been a great start for this very challenging conversation. And I really like the sound of that. Maybe in the future we can say you can call your friendly neighbor toxicologist and have it on a speed dial so you can get the information you need to feel comfortable and informed about the decisions you make to keep yourself and your family safe. So thank you again, Dr. Solomon. We learned today that the doses makes the poison, that a hazard does not equal risk, and that our planet Earth and all its organisms are collections of chemicals. Yes, chemicals, a term that is well understood in the sciences, but that often conjures up a concern in the eyes of the public, especially when reading a label on a medication or even a common household product. We all want to be safe and stay healthy. And while it is true that we need to be very careful with some chemicals, most chemicals are relatively harmless, and many are essential to maintaining health and quality of life. So hopefully now, instead of just having the alarming response to the words hazard and chemicals, we can now follow those with questions about what is the doses and what is the risk. Thank you again for joining us on another lecture of the Elements of Sustainability series. Until the next one.